to the presentation of this new project, which is about household waste classification. To set the context, I found this project on the Kaggle platform. There's no reward at stake, it was simply a learning project, so that's it. I'll add the link later in the project details section if you want to check it out directly. So, to quickly summarize the problem statement for you, you should know that every year we produce more than 2 billion tons of municipal waste worldwide. But among these 2 billion tons, only 13.5% of the waste is recycled, meaning the remaining 86.5% ends up in landfills or in nature. And every year, 8 million tons of plastic waste end up in the ocean. So, this problem highlights the inefficiency of our sorting systems, knowing that manual sorting is not only slow and expensive, but it's also prone to many human errors that compromise the quality of recycling. To offer a solution to this problem, the platform has provided a collection of waste images grouped into 6 categories. There are a total of 2,527 images for the 6 categories, so without a doubt this is a hands-on application of deep learning that we have here. So, to address the problems raised, we used neural networks, and it's true that 2,527 images for neural networks is very little. The platform also offers a dataset of up to 25,000 images, but that would require a lot of resources. To give you an idea, when training a single model with the 2,527 images and a GPU processor, it took me almost an hour just for the training. And you have to test several models to keep the best one in the end. So I'll let you imagine how long it would take me to train with a dataset of 25,000 images. But since this is a project that will only stay within another group, I think we're already doing pretty well with the 2,500 images, and we can definitely come up with something interesting with that. So to get back to the topic, the 6 classes are the ones you see here on the screen. And according to the data description on the platform, we have about 393 images of cardboard, which correspond to cardboard packaging, 493 images of glass for bottles and glass containers, and 400 images of metal. For example, for cans and metal tins, there are 584 images of paper and 127 images of general waste or even food scraps. The goal of this work is to develop an application that will help us sort our household waste. Simply by filming the object, the application will tell us which bin to put it in. It should also be noted that the images have varying resolutions. Additionally, the uneven distribution of classes is a warning sign for underfitting or overfitting. So we will propose some solutions to overcome these problems. And these solutions are explained in the next section, which is data preparation. Before anything else, since the images we have are of different resolutions, I'm not sure if you can tell the difference between this image and the next one. Well, to illustrate things a bit, we took an initial image in the form of vertical rectangles, here. And after applying resizing, we have an image a bit more in the shape of a square. And it's the same for the image below. Here, it's in the shape of a horizontal rectangle. And the ultimate goal is to have all our images at the same resolution. So why do we standardize our images to 224 by 224 pixels? It's simply a standard size for many pre-trained models. Next, pixel normalization was also applied to the images. And you'll see in most articles that the normalization values for the mean and standard deviation are the same because they come from the normalization values of the ImageNet dataset. So ImageNet is a massive database of 14 million images created for research in computer vision and machine learning. And so these transformations applied to our images can simply improve the performance and convergence of neural networks. As for data augmentation, we only have 2,527 images. Our dataset is considered small by deep learning standards, where datasets with millions of images are common. So to address this limitation, we will apply data augmentation techniques that artificially increase the diversity of training examples. So data augmentation is simply when you take an image and apply a random horizontal flip to it, for example, or a slight rotation of a few degrees to get different viewing angles. There are also variations in brightness and contrast that can be applied to the images. These transformations allow the model to see a greater variety of examples during training, improving its ability to generalize to data it has never seen before. For this project, we use convolutional neural networks, which are particularly well suited for image classification. And I don't know if you noticed at the very beginning of the video, but some image classes are less represented than others. And so this class imbalance caused our first model to overfit. If I remember correctly, we only had 127 images of plastic compared to 584 images of paper. So the model developed a bias toward the majority classes, which somewhat compromised its performance on the underrepresented classes. To put it much more simply, actually, the model memorized the data it saw during training and lost its ability to perform well on new data. So to address this problem, we had several methods available, such as oversampling or undersampling the classes, for example, which might be an initial instinct. But we chose to go straight for a more effective method, which is dropout, a technique that involves randomly deactivating neurons during training, forcing the network not to rely on specific connections and to develop more robust representations. You'll see in the notebook that this still significantly improved the model's performance. But we didn't stop there. We also tried transfer learning, which turned out to be extremely effective. Transfer learning is an approach that involves leveraging models pre-trained on large datasets to solve specific tasks with much less data. And for that, we used models like EfficientNet and ResNet. Finally, for hyperparameter optimization, we used Optuna. And yes, you'll see in the notebook, for this part, a large number of errors are displayed. In fact, I had to stop the model while testing different parameters, because it would have taken an enormous amount of time to test all the parameters. As a result, the model that was set up in Streamlit is not the best model with the best parameters, but rather the second to last model, which still has a significant level of performance. We were around 98% accuracy and F1 score and 90% recall. So that's all for this short presentation. Thank you for your attention and see you very soon.